Hello, everybody, and welcome. For my talk called Some Like It Hot, I'm here to talk about how data fits along a temperature spectrum and how thinking about it that way is actually really useful when selecting which kind of data system you want to use. I'm also going to talk about how thinking about this temperature spectrum provides the key to that question you've always been asking yourself. How come it seems like I can never find the perfect system that solves all my problems? So, who am I, and why should you listen to me? Well, I'm Gian Merlino, and you don't have to listen to me if you don't want to, but why you might want to. I'm committer and PMC chair at Apache Druid, which is a big data project used at some of the largest internet companies today and a variety of other industries as well. I'm a co-founder at Imply, a company built around Apache Druid, and we're hiring, so please feel free to come talk afterwards if you're interested. And I've been working for the last decade or so on scalable data systems, and a lot of that's been spent in the analytics space. So it's a space I'm definitely very interested in. So today, what are we going to talk about? I'm going to talk about how data fits along that temperature spectrum that I was talking about earlier, from cold to hot. We're going to go on a tour of data systems over the years and talk about how things have evolved, how they've scaled, all that. The project I work on, Apache Druid, we're going to meet Apache Druid and see how it fits into the space. And then we're going to ask ourselves, can we have it all? The thing that we're always wondering, is there one system that does it all? The answer is, of course, maybe. So first off, what are things you might care about? Well, the spectrum, as you might have guessed, from cold to hot, is a spectrum mostly about performance. But there's other things that relate to performance and how we think about it. So on the top, we have this beautiful bowl of hot Cheetos and Takis representing hot data. On the bottom, we have a warehouse of government cheese. It's even in black and white, representing cold data. Um, for hot data at the top, we're thinking query speed sub-second to just a few seconds. We're generally going to want to be working with data as fresh as possible. It might be true real time, might be near real time, might be data that's loaded within the past few hours, but in generally we want to care about fresh stuff. We're going to have high concurrency. So these hot data sets are data sets that part of the reason they're hot is because they're so critical to the business that we want to put them in front of a large number of people, not just professional data people, but end users, product managers, marketers, that kind of thing. And the use cases are going to be highly interactive. So people are going to be spending a lot of time inside these tools. They're not just going to be getting a report and leaving. They're actually going to be doing a lot of investigation. We call this OLAP, online analytical processing. On the other side of the spectrum, the other extreme, cold data, slow queries are okay. We might not care how slow they are. We might be okay with minutes or even hours. Less fresh data is okay. We're doing a lot more reporting, a lot less operational stuff. Generally going to be low concurrency. We're not going to have that many people using this. It might just be our professional data people. And the use case is more oriented around reporting and planning, less around being highly interactive. So this is a tool that we make at Imply. As you might have guessed, at Imply and the Apache Druid project, we're all about hot data and fast stuff. And so this is a tool we make called Imply Pivot. It's the making a tool like this work properly is actually what inspired us to create Druid in the first place. We wanted to build something that was able to power this kind of interactive experience, even at scale, even on massive amounts of data. And why does this matter? What do people do? Why does this ability matter? You might call this real-time OLAP. And the two use cases that fit into it are exploration and monitoring. Exploration meaning I want to drill into my data, I want to do iterative questions, I want to understand what's happening. And then monitoring meaning I want to know what's happening right now, observability. These two things come together to build these real-time OLAP workflows. So that being said, where does it matter? These hot speeds are useful in a variety of applications. Some of the ones that we've seen people adopt Druid for are the stuff on this slide. So risk and fraud analytics, useful because there is a need to dive deep into things to figure out what's going on. Data-driven applications is a really big one. That's a case where concurrency is going to be very high. You might have a large number of people outside your organization accessing a data-driven application. Network performance, another one that tends to be very operational in nature. The real-time, fresh aspect of things tends to be very important there. Click streams, similar situation. Freshness matters for understanding rollouts of new products, doing A/B testing. But even the ability to do a lot of exploration over historical data is very interesting when trying to find trends and figure out what your users are doing and how they're behaving. Digital advertising, the market everybody loves to hate, although it did bring one nice thing to the world, which is it's been the genesis and inspiration for a lot of interesting technology that we see around us in the big data world. And Druid's actually no exception. Druid was originally created for a digital advertising problem. It's a space where there's even the smallest players, even the smallest advertising companies generate a truly tremendous amount of data. And so the need for tools that are scalable and efficient is immense. So we can at least thank them for that. Data warehousing, a situation where you might have a data warehouse that you're looking to expose to more people, you're looking to make it more real time, you're looking to get more applications built on top of it, and so you're looking for a platform to make that happen in a performant and available way. Metrics, so your sort of time series metric store type applications. There's actually a lot of overlap between the time series world and the analytical world. They're coming into a collision over time, I believe. And then IoT, we've seen it come up a lot there as well, where the number of devices can be truly incredible. So these are all a variety of situations where the scale, concurrency, number of users you want to get in front of, amount of exploration that needs to happen, amount of observability that needs to happen, mean that you want to treat them as hot. So that demands a question, which is why do we want to tolerate cold data at all? Why not make everything hot? And of course, the reason is cache. The reason is that making large amounts of data available at hot speeds is something that costs money. It requires memory, it requires hardware, it requires network bandwidth. And the business case to spend that kind of money may not be there for everything. So let's take a little bit of a stroll down memory lane and look at the architecture of these systems and how some systems evolve to become hotter, some systems evolve to become colder, and what drives that. It all starts at the beginning. It all starts with a single relational database, one size fits all. You've set up Postgres. You're using it to store your shopping carts. You're storing your products in there that you're selling on your e-commerce website. And it works great. You're doing your analytics on your production database because you don't have that many customers yet. Why not? You don't have that much data. But at some point, this stops scaling well, and you stop being able to use a single database for everything. So the next thing that's going to happen is you're going to build a data warehouse. You're going to build a data warehouse. You're going to have your relational database is now going to only be used for what we call OLTP, online transaction processing. It's only going to be used to power the actual application or the actual business case that you're offering. You're going to develop some sort of ETL, extract, transform, load process. I apologize for the acronyms, but this is an area that's rife with acronyms. You're going to load that into your data warehouse. And your data warehouse is something that's going to enable you to do really the same kinds of analytical queries you were doing on your single database. But by offloading it, you are minimizing the production impact of doing these analytical queries. And you are potentially getting the ability to do these analytical queries in a more scalable way. But one of the issues with the old school data warehouses is, you'd have a tough time scaling them too. You would put a lot of data into them. They would get slower and slower and slower as you added more and more data. And eventually they'd be too slow to really use in the way that you want to use them in. They become ice cold. And you want to warm them up a little bit. And so the way that people back in the day would warm them up a little bit is put things into a OLAP database, an online analytical database. And this would be a subset of the data. It might be a summarized version. It might be just a few tables. It might be coarser granularity, like you might only have daily aggregates instead of having the raw data. But you do something to it to make it more manageable and put it into an OLAP database. And now that's hot again. And now you have your situation where in this architecture, which was very popular in the 90s and early 2000s, you have a data warehouse where you have sort of all your data cold, but it's all there. Your OLAP database where you have some of it, or maybe it's summarized, or maybe it's not full fidelity, but it's available hot. And then big data happened. Then we hit the mid 2000s, we hit 2010. It's time for big data, and everything started to scale out. Your single relational database, no one's doing that anymore. Now everybody has sharded relational databases. Instead of putting all your shopping carts and products in one database, you're going to split them up by customer. Um, Instead of having a data warehouse, now you have a data lake. And your data lake is going to be either a Hadoop-based data lake using HDFS, it's going to be a cloud data lake using S3, something like that. It's pure storage. Um, Getting data from the thing that runs your business to the thing that you're going to store it in, you're going to have some kind of ETL process again. Could be change data capture plus Kafka. So it could be that you can use, for example, Kafka Connect to capture change logs from your relational database and dump them into Kafka and get them from Kafka to a data lake. There's a lot of ways to do this, but one way or the other, you're getting it in there. And then you have a scaled out query engine. And the scaled out query engine enables you to do the same kind of analytical queries you could do from your old data warehouse, but now you can do it from your data lake. So everything's scalable here. The sharding allows you to scale out the transactional database to your heart's content. The ETL processes are all scalable as well. The data lake is, of course, scalable storage, and then the query engine is scale-out processing. So everything's scalable and beautiful, but it has a downside. It's slow. It's actually really slow. It's actually slower even than the old system. It's more scalable, but we've sort of paid a devil's bargain to get that scalability. We've slowed everything down. Now we're in the world where we're using query engines like Hive and like Presto, and they work well enough, but these queries on large amounts of data are taking quite a long time. So something that a lot of people start doing, and this becomes popular, really popular in the mid 2010s, just a few years ago, is storing an optimized copy of your data in a serving database. One of the earliest things that got really popular for this was Cassandra. HBase was also pretty popular. These serving databases are going to store an optimized copy. This will sound a little bit familiar. It's a little bit similar to the technique used in the pre-big data era with the OLAP databases. These serving databases are going to store some kind of optimized copy of your data designed for hot access. A lot of the ways that people did this, like I mentioned in the early days of big data, were with key value stores like HBase and like Cassandra. And this is where Druid comes in. What we've done with Druid is we've tried to build the best serving layer that we could possibly think of. And that means a few things. It means that we are targeting very high concurrency. We're targeting very low latency queries, but we're also targeting a lot of flexibility in the kinds of queries you can do. So one important thing about Druid that we'll get into in a few slides is that it's actually not a key value store. It's based on a underlying column-oriented data store. So it's the same kind of columnar storage that you would see in a data warehouse or something like an orc file or a Parquet file. But on top of that, we've added indexes. We've added the ability to do streaming ingestion. We've added the ability to do batch loads from data lakes. And we've added a whole suite of resource management features that are designed to give you the kinds of performance you're looking for, even under highly concurrent workloads. And what that means is that in your data architecture, Druid is going to fit into this hot analytics area of the stack. You may still be using a query engine for your colder data and your warm data, query engine like Presto, like Hive, like a cloud data warehouse. And you'll be using Druid for things that have these hot requirements. One interesting thing there, of course, is why don't you use Druid for everything? Why don't you use a query engine for everything? Why does it make sense to have both? And we'll talk a little bit about that in the later slides as well, as we start to explore this idea of why can't we have it all? Can we have it all? Where are we getting with this? But I'm getting ahead of myself for now. Let's just talk about Druid. So the reason people use things like Druid is because they're looking to power analytical applications. And it's especially interesting to use a technology like this for analytical applications, because if you have any of the problems of scale, of high concurrency, of streaming ingestion, of wanting to provide people with a lot of observability, but also the ability to do a lot of ad hoc exploration, it's really important to have a system that scales well, that performs well, that's able to power that stuff. So people have put a lot of applications on top of Druid over the years. On the left, of course, you have the one that we built at Imply, Pivot. On the right, there's other applications that have official support added for Druid, Looker, Metabase, Apache Superset. SQL, of course, not an application, but you can query Druid using SQL, and you can use that to make your own custom applications. Druid is used pretty extensively in the wild. The project's been around for a few years, and a lot of the earlier and biggest adopters were tech companies in Silicon Valley. And of course, the reason for that is because these tech companies are some of the first to have these big data problems and to have these big scale problems, and some of the first to adopt technology designed to solve it. So Druid used at Netflix for real-time insights on experience, used at Mopub, which is a Twitter subsidiary, for querying terabytes of data in seconds, and used to power analytics at Airbnb as well. What all these use cases have in common is they're huge and performing very well. So ingesting 100 plus billion rows per day, retaining trillions of rows, year of retention, hundreds of servers, query latency sub-second to a few seconds, and a mix of streaming and batch ingestion. And these kinds of folks are using Druid because it's fast, it's fast. We do a lot of internal benchmarks, of course, but the ones that you should trust most are the ones done by third parties. And this is some data from a benchmark done by an academic database research group showing performance of Druid on similar data sets versus Hive and Presto, some SQL query engines. And you can see pretty massive differences here, 20 to 59x over Presto and 100 plus x over Hive. And so what's going on here? Why does this happen? Druid, I said earlier, uses a columnar format. Hive and Presto can read columnar formats as well. Druid is integrating with the data lake. Hive and Presto can integrate with the data lake. What is the reasoning behind this? So to figure that out, we have to pop the hood and ask ourselves, how does it work? What's going on in there? So internally, Druid uses a microservice-y kind of architecture where we have a bunch of different processes responsible for a bunch of different things. And I don't want to go into a ton of detail about how each of these works, because I don't want to bore you to death, but suffice to say that you can get a full explanation in the docs. The part I do want to touch on is you see these little boxes everywhere, these little columnar yellow boxes everywhere. And these boxes are stored in deep storage and pushed in there by the indexers, pulled out by the historicals. These are processes in Druid responsible for reading and writing data. And what these little boxes are is we call them segments, data segments. Each one is a few million rows and is essentially a micro partition of the data set. So a really big data set is going to have thousands or tens of thousands or even millions of these segments. And what they give us is each segment is individually compressed and indexed, and the parallelization system in Druid is built by fanning out queries to all the segments involved in the thing you're trying to do. And then what happens inside them is really where the magic happens. So we built the fan out system just to fan queries out to thousands of segments per query. And then within each segment, we try to process those 5 million rows as rapidly as possible. And that's the key to performance. So I'm going to talk a little bit about a sample query and how it operates on the scale of a single segment, and then imagine that happening 1,000 times in parallel to get you the answer you need. And to do that, I want to talk about how the engine and data format are integrated. So there's a few things I'll talk about. One is compression. In Druid, we have a columnar format. Every column is individually compressed based on that type. Secondary indexes, that is one area where we start to differ from what a lot of query engines do. A lot of these query engines and query data lakes don't have secondary indexes, but it turns out to be very powerful. Operating directly on compressed data is also really important. Some of them do it to varying degrees. And late materialization is also critically important. This is a fancy database person term for saying don't read data you don't have to read, which is going to be a really common theme, as we'll see. So this is the layout of a Druid segment. A typical Druid segment is going to have a few million rows in it. This segment has 8, because that's how many fit on the slide. This segment has 5 columns. So in Druid, we store data oriented by column. The first column here is time. You can see it's long typed, 64-bit integer. The second column is artist. So imagine this is a table of ticket sales in various cities or various musical acts. So we've got AC/DC, Silverchair, we've got Perth and Sydney. The artist column is a string, and there's 3 components to it. The data component is, there's one entry there per row, and it's just an integer. So you see the first three are zeros, the second two are ones, and the next is 222. So what this is saying is it's a dictionary encoded string values. And so the first three rows being 000 mean that the first three rows of this particular data set have artist AC/DC in every of the first three rows. And then the next two are both Kylie, and then the three after that are Silverchair. We do this so it's a form of compression. So it makes the data section smaller, especially when the number of unique values is low relative to the number of rows in the segment, which is common for a lot of columns. It's not universal, but it's common enough that this is quite helpful. But it doesn't just perform compression, it also enables us to operate on the compressed data. So you'll see in a bit, but what we do is when we're doing a group by artist or group by city, we're going to actually use these numeric keys to do the grouping rather than the strings, because we can process numbers faster than strings in a computer. The next section is the dictionary. The dictionary tells us what each dictionary code means. And then the third one is the index, and the index helps us filter. So what the index is saying is there's going to be a single entry in the index for every entry in the dictionary. And they're corresponding one-to-one. And it's a list of rows that contain that particular dictionary value. So the first section of the index is which rows have AC/DC and so on. These are also stored compressed. They're stored compressed using an algorithm called roaring bitmaps. And we also operate on them in their compressed form. So if you want to do an and or an or comparison, we are actually going to combine two compressed roaring bitmaps together into another roaring bitmap. And finally, the last two columns, skip city. So the last two columns, price and count, are both numeric columns, just like the timestamp column. They're stored the same way. All right, let's do an example query. So here's a simple query. We want to look at all the ticket sales for AC/DC, and we want to break it down by city, group by city, and we got to get the total price in every city. Straightforward. So a query like this is actually a typical kind of query you're going to do with a system like Druid. You're going to be doing some kind of filtering, some kind of grouping and breaking down, and then some kind of aggregations. These are the kinds of queries that are going to power these interactive analytic experiences we're trying to power. And we want to be very flexible in the kinds of queries we can do. So we want to be able to support any kind of filter, any kind of grouping, any kind of aggregations. And so because of that, we're not going to want to pre-cache anything. We just want to focus on computing whatever you give us as quickly as possible. So the first thing we're going to do is resolve the filter. And so we're going to go to the dictionary, and we're going to see what the code is for AC/DC. The dictionary is stored in sorted order, so we don't actually have to read the whole dictionary. We can do a binary search through it to find the correct value, which is what we do. We see that AC/DC is 0. The next thing we're going to do is retrieve the index for that value. So that's going to be the first row in the index section, because it's the first row in the dictionary section. And what we're going to see is we get a compressed bitmap that represents 0, 1, and 2. So the first 3 bits being set, representing the first 3 rows containing that value. So now we know which rows contain this value. And this is actually super important. This is one of the first ways that we start to differ from what a standard query engine on a data lake would do. A lot of them don't do secondary indexes because the way that you need to use secondary indexes involves a lot of random access, and it requires data actually being stored on the server. And we'll discuss this more in a bit, but Druid's actually prefetching all this data before the query happens. So it has the data stored locally, typically on SSDs with however much cache memory that you can. Doesn't need to all be memory, but we typically use a mix of memory and SSD. And we are able to, because of that, we're able to use these indexes. So, okay, anyway, we use the index. We know that rows 0, 1, and 2, the first 3 rows qualify for the filter that we're looking for. The next thing we're going to do is the aggregation. So next we're going to group by city and sum up price. And so the way we do that is now we go to the data section of the city column. You can see we have not gone to the dictionary or the index. There's no need. We just need to know what the first 3 dictionary values are. And it's 2, 1, and 2. And the first 3 prices are 1800, 2912, 1953. So we're going to build a little array, and we're going to use that array to aggregate these things. And the reason we're doing an array is because there's not that many cities. There's only 3. And so what we're going to do is we'll build a 3-element array, and then anything we see for one of the cities will go in that element of the array. If there was a lot of cities, more than we could allocate an array for, then we would use a hash table. So we choose hash table array based on how many things we anticipate grouping. Anyway, so that being said, we've chosen an array because there's not that many cities. It's going to have 3 elements. Because we don't know ahead of time what cities we're going to see, but we know there's only 3. We're only going to see stuff for Perth and Sydney, so only those 2 are filled in. Melbourne has a null stored in it. And that's the end of that. We don't have to read the rest of the data section of the city column because we know from the index for artist that only the first 3 rows contain anything we care about. We don't need to read the dictionary yet because we don't actually care what the city values are yet. We're just aggregating. The next thing we're going to do, now we're going to read the dictionary. We've done aggregation, and now we read the dictionary to see what the actual values are. And we do this after aggregating because typically when we're doing a group by, a lot of times the output of that group by, the number of grouped rows, is much smaller than the number of rows you're reading. And so it pays to defer this dictionary lookup until later. So this is this idea of operating on compressed data as long as possible. Anyway, at this point, we know that Perth and Sydney are the 2 cities, number 1 and 2, that we've seen tickets for. And so we can, at this point, we are done with the query for this segment. And let's look at what we've done. We've done a binary search through the dictionary section of one of the columns. We haven't looked at the entire dictionary even, we've just looked at pieces of it. We've done a single random access to the index section of that column. We have read just the sections of the city and price columns that we need based on the index of the artist column. We haven't read past the first 3 rows because we didn't need to. And we've only read the 2 values out of the dictionary using random access for the city column. So we've really been very economical about how much data that we've read from disk, from memory, how much we've had to transfer to the CPU, all this stuff. And this is where we get our performance from. We get performance from being extraordinarily economical about how much data to read and process. And then once we've processed each segment in an economical way, from every segment we have a partial result, and then we just have to merge them all together. This process in a well-running, smoothly humming Druid cluster, even on top of billions upon billions of rows, is going to happen in less than a second. But okay, I at the beginning promised to talk about why it seems you can never find the perfect thing. Can we have it all? And let's talk a little bit about that. So we have Druid, and I talked about why Druid's super fast. We're familiar with query engines, things like Presto and Hive. Why can't they do what Druid does? And why can't Druid do it? And why do you still need them in a world where Druid exists? Let's look at some of the differences between them. With Druid, we're doing batch ingestion and streaming ingestion. We're actually ingesting things because Druid is not just a query engine. It's a database that stores a copy of the data. With Druid, data is fetched ahead of time, partitioned and indexed, and this ahead of time fetching, this indexing, this well partitioning and balancing of the data all contribute to performance that is beyond what a simple query engine on top of Data Lake is going to be capable of. The query engine on Data Lake has one big advantage in that it does fetch data on demand. And fetching data on demand means a couple of nice things. It means you don't have to ingest it first. So if you have data in some goofy format to query it in Druid, you have to go through an ingestion process. Something like Presto can query it directly. It's not going to be very fast to do each individual query, but it may be quicker to get off the ground in the first place because you don't have to load a table first. This ability to fetch on demand also means that the elasticity can respond much more quickly. So Druid is an elastic system designed for the cloud, and you can scale it up and scale it down. Scaling it up is as easy as adding more processes. Scaling it down is as easy as terminating them. And the system will self-balance and self-heal in response to this scaling activity. So Druid is a totally elastic thing, but because we need to fetch data ahead of time and because we do have to balance data before a new server can be used, when you add a new Druid server, that server doesn't participate in queries for generally a few minutes to an hour or so. And what that means is that if you're elastically scaling it up, you will scale it up and you'll be able to use that new capacity. It'll take at least a few minutes for it to become available. Whereas a simple query engine that doesn't have any locally stored data, you could imagine spinning it up, doing a query, and then torching it down. So the elasticity can respond a bit quicker with that kind of system. Both, of course, have elasticity. They're both fault tolerant. They're both share nothing in the sense that the servers don't coordinate with each other, and they're both scalable to a very large degree. So it seems like they have a lot in common. And these differences, a lot of it comes down to, are we fetching data ahead of time? Are we indexing it ahead of time or not? The use case for Druid is you're going to get better performance on the same hardware. That prefetching of data, the indexing, the increasing efficiency. So the price performance ratio is really great with Druid. You're also going to get a lower performance floor. And what I mean by that is that you'll be able with Druid to get queries that are sub 1 second, even sub a few hundred milliseconds. Whereas with a query engine on top of a data lake, it's going to be really tough to get their query latencies that low. But the query engines are nice. You can have a lot of federated data sources in there. You can query things that were not previously ingested into that query engine. And you get spot elasticity. You get the ability to elastically scale up and down very rapidly. So, can we have it all? The thought I want to leave you with is that while the use cases are very different, the architectures are not that different. We have relatively minor differences, like are we prefetching data or not? Are we fetching data on demand? Are we able to query data in something other than our native format? Are we building secondary indexes or not? Are we intelligently balancing or not? One reason that I really enjoy working on Druid is because I think it is a good platform for exploring these ideas. And I think it is a good platform for eventually building a system that is going to be able to let you have it all. And while we might not have that today, it's a world that I'm really excited about working towards. And with that, thank you, and any questions?